Hi everyone, my name is Adam, and today I'm going to be presenting our machine learning project, Chest X-ray Pneumonia Detection with Attention Mechanisms. So first of all, let's talk about briefly about our problem statement. It's basically that pneumonia is a leading cause of death worldwide. It's particularly affecting vulnerable populations like children under 5 and elderly adults over 65. And according to the World Health Organization, which is the WHO, pneumonia was actually responsible for over 800,000 child deaths in 2017 alone. And that's approximately 15% of all deaths in children under 5. So when it comes to tackling this issue, there are basically traditional ways of diagnosing pneumonia, and they all rely heavily on X-ray, chest X-ray diagnosis by radiologists. However, there are main issues facing this, or like three main challenges. The first one is that it's time consuming because it's basically in our modern era, we need rapid screening in order to be able to diagnose these diseases. Second one is that it's subjective. And so actually studies show that even experienced radiologists have inter-observer agreement rates of only about 70 to 85%. So that means that radiologists disagree on diagnosis up to 30% of the time. And thirdly, there is a shortage of radiologists in many regions, making healthcare inaccessible basically to a lot of people. So right now we're going to basically talk about all the related works that we found that tackle this issue. So actually we've done extensive work and we've looked into multiple models which are shown here in this slide. And we decided to basically, actually I need to find the slide. Okay, it's right here. Yeah, so we've looked into a variety of models like Exception, GoogleNet, ResNet, DenseNet, etc. And we decided to settle on a combination of DenseNet and CBAM, which is a convolutional block attention mechanism. And the main reason for that is because of its very good accuracy. As we can see, it's 83%. Meanwhile, it's a relatively smaller model, so the number of parameters is smaller, which is 9.7 million parameters, compared to other ones that here we can say is 42 million. In other cases, like the VGG model, it has even more than that, approximately like 160 million, I believe. So that's the main reason we chose this specific model. And right here in the same slide, it shows the architecture of this model, which basically incorporates the CBAM module at two different instances into the flow of data through the model in order to be able to better classify uh, a certain X-ray image as either normal benign or as a pneumonia image. And yeah, so that's pretty much our baseline. And so far, we've basically managed to correctly implement it on Google Colab. And in order to do that, basically, we had to implement the DenseNet 121 backbone, which is the original model, and then implement the convolutional block attention mechanism in the form of modules that are integrated. So the model DenseNet 121 is actually pre-trained on ImageNet data, and basically we're leveraging transfer learning in this case. And on top of that, we integrated the CBAM module after each of the four dense blocks. And this module works through two mechanisms, which is the first one is the channel attention mechanism with a squeeze excitation ratio of 16, and this determines what features to focus on. And at the same time, we have the spatial attention mechanism, which uses 7x7 convolutions, and this determines where to focus in the image. And we have another critical method called get attention maps, which basically extracts the attention weights from each CBAM module. And obviously, we created a training loop in order to be able to train this model iteratively through a number of epochs. And actually, we faced a few challenges when it comes to epochs, which Adam is going to discuss later on. But basically, we had to keep our number of epochs to be quite low in order to get some sort of performance without timing out on the Google Colab environment.
We also added data augmentation for the normal class since we had an outnumbered class by a ratio of 3 to 1, which was the pneumonia class. So our model couldn't really classify the normal class because of this issue. Moreover, for our initial results for the baseline model without any modification, we got an accuracy of about 73%. The model performed poorly due to not having enough normal data. So it usually just classified everything as pneumonia, making it have a really high recall for pneumonia and a really low precision, while having a really high precision for the normal or a moderate normal precision with a really poor recall. However, after implementing augmentation to the normal class and adding the weighted loss function, the results improved marginally. We got an 87% accuracy with about 99% recall for the pneumonia since it was the outnumbering class. But it also had a moderate precision of about 77%, if I recall correctly. However, for the normal class, the precision kept on being really good in the 90s, while the recall remained moderately poor. It was in the 60s, 67%, I believe, which made this really difficult to find solution. Moreover, I think in the next milestone, we should oversample the normal class to account for this error. For our AOC and ROC, we got a 0.9 AOC, which is really good with an 87% accuracy.
As to the next steps and timeline, basically the main features that we need to implement are first the multi-scale attention fusion, which we intend to implement by week 4, which is the November 1st. And basically our implementation is going to consist of applying CBAM at multiple feature resolutions and also implementing a feature pyramid attention mechanism, as well as fusing attention maps from different scales. The second thing that we need to work on is progressive attention training, and we intend to do that by the 5th week, which is November 8th. And basically, we intend to do that through 4 phases in training by freezing and unfreezing the CBAM modules at different stages. After that, we intend to complete the implementation of our loss function, hybrid loss function that's weighted. We already added the class-weighted cross entropy loss, but we still need to add the attention regularization and the attention sparsity loss. Both of these are losses. Basically, after that, we intend to work on tuning our parameters and evaluating them against the other versions that we get. And that's basically going to allow us to get the optimal version of our model on our specific data set after augmentation and implemented all of the loss functions.
Finally, for each team member's contribution, Adam visualized the data after training the model and was also training the baseline model and implementing it in Collab, while I implemented a model with augmentation to account for the skewness of the dataset. After that, I implemented another model with the loss function since the result with only augmentation were still moderately poor. That's it. Thank you.